14 miles southwest of Plymouth, the Eddystone Rocks sit directly in the path of ships entering the English Channel. It is a submerged granite reef, constantly battered by Atlantic gales and powerful eddy currents. Building on this reef meant fighting the tidal cycle. Crews had only a few hours of exposure at low tide to work on the slippery, sloped granite before the ocean reclaimed the site. The first attempt to mark this hazard was Henry Winstanley's 1698 timber lighthouse. Designed using Baroque aesthetics, he prioritized ornamental complexity, wrapping the exterior in ladders, scrollwork, and a massive weather vane, drastically increasing the surface area exposed to wind loads. During the Great Storm of November 1703, the structure reached its breaking point. Extreme wind shear shattered the skeletal timber frame, sweeping the entire lighthouse and its crew into the sea. John Rudier tried next with a ship-built conical tower. His design successfully resisted the hydrodynamic forces of the reef for 47 years, but its reliance on heavy oak timbers proved fatal when the lantern caught fire in 1755, burning the structure to the waterline. The search for a permanent solution led to John Smeaton, a scientific instrument maker who approached engineering problems through rigorous empirical research rather than established trade customs. Reviewing the destruction of the first two towers, Smeaton deduced the specific requirements for survival on the Eddystone. The structure had to be completely non-flammable to prevent another fire, demanding solid stone, yet it required the structural resilience and cohesion of a timber ship. The resulting structure, the third Eddystone Lighthouse, would signify a transition in the building trades, moving toward the rigorous, evidence-based discipline of civil engineering. Any offshore structure faces a core mechanical conflict. The vertical load of gravity must anchor the building, while it simultaneously withstands the massive horizontal shear forces exerted by Atlantic gales and breaking waves. Smeaton looked to the natural world to resolve this tension. He modeled the tower's profile after the Quercus robur, the English oak tree. The oak derives its stability from a flared base. This shape gives the tree a low center of gravity and provides a wide, expansive surface area to anchor its root system firmly into the earth. The sweeping inward curve served a hydrodynamic function, directing kinetic force upward and away to dissipate impact. Compare this to Rudier's conical design. Water strikes a flat plane with nowhere to go, transferring kinetic energy directly into the masonry as destructive horizontal shear force. To handle the remaining stress, Smeaton optimized his material distribution. He constructed the tower's exterior skin using local Cornish granite, selected for extreme durability and resistance to the abrasive action of salt and sand. Inside this protective shell, he built a core of Portland limestone. This stone was easier to work and less expensive, providing the sheer mass and inertia necessary to keep the building anchored under severe impact. By treating the tower as a monolithic entity shaped by natural forces, Smeaton established the geometric standard for subsequent wave-swept lighthouses. Traditional masonry relies on gravity and friction between stacked blocks to hold a wall together. In a wave-swept environment, those forces are quickly overwhelmed by the lateral pull of the ocean. To ensure absolute precision, Smeaton set up a shore-based yard in Mill Bay. Every block was pre-assembled and checked on land, minimizing the time workers spent exposed offshore. His solution for lateral stability was a horizontal interlocking system using dovetail joints carved into the granite. Once slotted together, the geometry physically prevents movement. A single block cannot be displaced by a wave without dragging the entire course of stone with it. To counter vertical shear forces that could lift the blocks, Smeaton pinned the stacked courses together using marble dowels, chosen specifically for their high shear strength and resistance to saltwater corrosion. He then applied hoop tension to the structure. By embedding wrought iron bands around the circumference of the courses, he effectively pre-stressed the masonry, squeezing the blocks tightly inward. Finally, the structure was married to the earth. The base course was locked directly into corresponding dovetailed recesses carved straight into the native rock of the Eddystone Reef. Mechanically interlocking the granite across 3 dimensions eliminated the structural weak points of individual blocks. Smeaton have engineered a single unyielding artificial rock. The final bottleneck was chemical. Traditional mortar needs air to dry. If submerged before setting, the water dissolves the binder, making underwater foundations impossible. At the time, builders operated under a persistent misconception. They believed the physical hardness of the source limestone dictated the final strength of the mortar. Smeaton tested this assumption and found it completely false. His experiments proved that hydraulic setting properties were entirely derived from chemical impurities in the stone, specifically reactive silica and alumina, the core components of clay. Searching for the optimal chemical profile, he identified the argillaceous, clay-rich limestones of the Blue Lias Formation as his ideal source material. The material is processed through calcination. Heating the limestone between 950 and 1250 degrees Celsius breaks down clay minerals, isolating reactive particles. When introduced to water, hydration begins. Compounds form calcium silicates and aluminates, creating a rigid crystalline lattice that is inherently stable underwater. This chemical process differs entirely from traditional mortar, which relies on carbonation, absorbing carbon dioxide from the atmosphere, and fails completely when deprived of air. Smeaton engineered a specific recipe to maximize this hydraulic set. He combined the blue lias quicklime with Italian pozzolana, a volcanic ash, and added ground brick aggregate to increase the reactive silica. The resulting material was remarkably strong. It achieved compressive strengths of around 3.6 newtons per square millimeter at 28 days, matching the performance of modern natural hydraulic lime 3.5. Smeaton had engineered the first documented use of modern concrete in civil engineering. This chemistry provided the necessary foundation for the harbors, docks, and bridges of the industrial age. When the third Eddystone Lighthouse was first lit in October 1759, its beacon came from a chandelier of 24 tallow candles. But beneath that modest light stood a structure capable of enduring the harshest maritime conditions. The tower stood resolute for over a century. By the 1870s, however, the lighthouse began to shake violently during storms. The interlocking masonry had not failed. Rather, the repetitive leverage of the sea had eroded the natural granite bedrock beneath it. With the foundation compromised, Trinity House commissioned Sir James Douglas to construct a much larger, modern replacement on a sturdier section of the adjacent rock. The cultural significance of Smeaton's engineering was already recognized. Rather than letting the sea claim it, the upper portion of his tower was dismantled stone by numbered stone, transported ashore, and re-erected on Plymouth Hoe as a permanent monument. The dovetailed foundation, however, proved entirely too strong to take apart. The original stump remains permanently anchored to the reef to this day, sitting quietly next to its successor. The lighthouse achieved a level of cultural enshrinement rarely afforded to infrastructure, even appearing on the reverse of the British penny for over 3 decades. By combining biomimetics, mechanics, and chemistry, John Smeaton moved construction from a trade of tradition to a science of evidence, becoming the first individual in history to claim the title of civil engineer.